In this video, we're going to look at the next example in section 12.1 and 12.3. So this is actually the fourth example in this section. All right, so here we're told to the right is the graph of the function z equals f of xy given by x squared plus y squared, together with the plane z equals 1, z equals 5, and z equals 9. So let's just go ahead and unpack that. So we see this purplish shape. That is our function f. And then these planes are those when z equals 1, when z equals 5, and when z equals 9. And so in the first part, what we're going to do is try to find the equations of the contours associated with these three planes. So what that means is we want to find the equation for these curves that we see that form when we intersect our function f with the plane. All right, so let's just rewrite here our formula. So we are given that z is equal to x squared plus y squared. So does this kind of equation look familiar? Well, you might have seen this before as r squared equals x squared plus y squared. So this equation is an equation of a circle of radius r. So now let's go ahead and plug in our z values to determine the equations of each of these contours. So when z equals 1, what do we get? Well, we get 1 is equal to x squared plus y squared. So what kind of shape is that? Or what kind of graph? Well, this is just a circle with radius 1. So now let's do this with the other z values. So what about when z equals 5? So we have 5 equals x squared plus y squared. So what kind of shape is this curve? Well, it's also going to be a circle. But now the radius, this 5 is what r squared is. So the radius will be the square root of 5. And so finally, z equals 9. We have that 9 equals x squared plus y squared. And here, this curve is just a circle with radius equal to the square root of 9, which is 3. Awesome. So those are the three equations for our level curves associated with the three planes given. All right, so now let's take a look at part B of this example. In part B, we're going to look at something called a contour plot, which is a really helpful way of representing a three-dimensional graph, which is a surface, because as you see, we just have a surface, two directions, x and y here, but on a flat plane. Okay, so to the right, we are given a contour plot of this equation we saw in part A, z equals x squared plus y squared. Note that the circles in the plot are not equally spaced. So we can see that. So we have circles going on, which is maybe not surprising for contours of the given function, but they're not equally spaced. So to get from the circle of radius 1 to the circle of radius, I don't know, what is that, 4? We go a certain distance between them, and then to get to the next one, looks like it gets smaller and smaller and smaller, the distances between those circles. Okay, what else are we told? We are told, or we are asked, what information does this give you about the function z equals x squared plus y squared? All right, so let's just make a couple comments about this contour plot and try to make sense of it. So we see that the curves we're given are all circles. Interesting. And that's what we saw in part A. All of the contours that we were given, no matter what your z is going to be a different circle, just with a different radius. Notice we have numbers on our curve, 1, 5, 9, 13. So these values are the z values associated with our function. So what that means is that this circle here is the level contour when z equals 1. So we can see those three level contours that we found in part A here with 5 and 9. Okay, cool. But what other information does this give you about the function? Well, one thing we can ask is about the steepness of our function. And just want to recall that you might have seen graphs like this before in the form of a map. So if you go hiking or something, you might be given, here's your hiking route. Maybe you make a loop, but then you're also given some other curves that happen. And these curves will tell you about the elevation. So these types of topographical maps, are exactly these kind of contour plots. We just don't call them contour plots when we're looking at a map. And so then it might be interesting to know, well, where is our function the steepest? So where is the surface or our function? Because if you were walking along on this kind of parabola surface shape here, where is it the steepest? So pause the video and think about that for a little bit. So let's think through it together. So it looks like these contours are 1, 5, 9, 13. So notice 5 to 9 is 4, a difference between 4. So 5 plus 4 is 9, plus another 4 is 13. So notice that as we get larger and larger in the z direction, our curves, our circles get closer and closer together. So what does that mean about the steepness of our function? Well, it must mean that our function is steeper there. So this means the surface is steepest farther away from the origin. And why is this? Well, this is because the contours are closer together there. They're closer together as we get further from the origin. So meaning if we're walking along the surface, we can go the same XY direction, but we're going to have to climb higher and higher, or our elevation gets more and more for maybe the same distance that we're going in the X and Y direction. So this is going to be useful as we do more work with functions of two variables, because again, this is a calculus class. So we're going to be interested in how functions change. So just like we evaluated with one-dimensional functions or functions of one variable, we might want to know, where is this function the steepest, or what are the rates of change of this function at various points? We want to ask those same questions of two functions of two variables. And so that's going to come up in the next sections of our workbook and class together. All right, great job working through these examples. Be sure to check out the rest of the examples and exercises in your workbook. Thanks for your hard work.